So I would like to argue that this theory is of large power. It's a mathematical psychological theory which is computationally tractable, which is easily for implementation into technology-enhanced learning systems. However, empirical validation of the structures for a given knowledge domain is very important, because we want to use, and I will show this later, these structures for adaptive assessment and personalized e-learning. And if you use the wrong structures which are not valid empirically, then of course you cannot get good results. So empirical validation is important. That's the reason that we have at the last topic of our talk today, empirical validation. And please have in mind these two diagrams which make understandable the power of the theory and which enable to remember all its main features. So if you once understood these two diagrams and how they are connected, you easily can derive all other important aspects of the theory from this. For instance, one important aspect is that the content and its structure induces the curriculum and vice versa. So in this case, for instance, the content and its structure is defined by the prerequisite relation. And the content, which is structured, induces the knowledge states and their structure on the right side. So you easily can derive from the structure of the content, in our case, the problems which have to be solved, the possible knowledge states of persons. Personalized assessment for efficiently identifying a person's state of knowledge, like in an oral examination by a private teacher, is possible, and that means you do not have to present all the problems. It's enough to have a subset of problems in order to assess, in order to diagnose a person's knowledge state. We will come to this later. We have, of course, not only individual goal states, for instance, this one or this one might be a goal state for learning and teaching. We also, of course, may have individual starting states depending on the pre-knowledge of a person. So that means we should at first have an assessment in order to figure out what's the pre-knowledge of a person, to assess which of the possible states is the starting state. If, for instance, a person already is able to solve the problems A, B, and D, it's not necessary to teach to solve these problems. You immediately can take this as a starting state for the learning and this, for instance, as a goal state. So pre-assessment of the knowledge state is very important in order to individualize the starting state, and furthermore, of course, the student, him or herself, and or the teacher has to define which is the aim of the learning, which is the goal state, and they have to agree on this. We already talked about the individual learning paths, which are also one big advantage of the theory, which make possible to individualize, to personalize the learning paths according to the needs and interests of the student. And it's possible by the knowledge states to characterize the learner's strengths and weaknesses in a given domain very precisely. In our case, by non-numerical characterization of the state of knowledge. And this, of course, is much more precise than, for instance, the evaluation in terms of level of knowledge, which does not give concrete advice what to learn next, how to compare the students in detail, and so on. Of course, if you take, for instance, the number of solved problems, you easily can have levels. However, this is not as useful for teaching and learning as the states themselves. The power of the theory also includes that you can make possible that the students have access only to those learning objects which the student is ready to learn. The student is neither overburdened nor underburdened. The challenge for the student is just okay. That means he might have high motivation, even may have the experience of flow. And of course, learning is very important for the student, and to have at least also some fun. As I told you, there are several possible learning paths. That makes it possible to have reasonable choices for navigation. We have no strict order, which might be boring for the student. There are choices for him or her. On the other side, there is no total freedom to choose. That means the student will not be lost in hyperspace. So I talked about already that the individualized assessment and efficient assessment might be very important. So we want to have an idea about the initial assessment, which in this first example is deterministic. I would like to explain the basic idea of this. The simplifying assumption is that we have neither lucky guesses nor careless errors in this example. And one principle is to pose a problem that is contained in about half of the knowledge states. That makes this procedure quite efficient. And the principle furthermore is to eliminate all the states that are inconsistent with the received answer. And we continue until there's only one knowledge state left in this process. So we take again this example, this structure. So what is aimed to figure out which of these possible knowledge states a student has. So we present him first with problem B, because problem B is in half of the number of these states. And in our case, in our example, problem B is solved by the student. So that means only those states where problem B is in are possible candidates for his or her knowledge state. We can skip all the states where problem B is not in. Next problem we present is the problem D. Problem D was not solved by the student. That means we can skip all the states which has a problem D. And again, using this principle, problem E is presented and it has been solved. And that means finally, after 3 steps out of 5 possible steps, because we have in this example 5 problems, after 3 steps we figured out that this student, giving these correct and incorrect solutions of the problems, has the knowledge state A, B, C, E. That means he or she is able to solve these problem types. When I talk about problem, I always mean problem type, because we think that several problems of the same type can be solved if the student has the appropriate knowledge. So please remember that problem means problem type, a collection of problems of equal difficulty or in some sense equivalence. So this is the result of our assessment, and we would like to introduce very briefly the basic idea of another approach for the initial assessment, the probabilistic approach. We want to estimate, or we start with a probability distribution over the knowledge space. And in our case, because at the beginning we do not know anything, we have the equal distribution. That means every state has equal probability or likelihood. We select a problem with about 50% probability. We update, that's another principle in this procedure, we update the distribution, the probability distribution, according to the answer of the student to be correct, whether or not the student was able to solve the problem or not. That is meant with the answer. And we continue until probability mass is mostly focused on one of the knowledge states. So let's try to explain this with an example again. The problem B is solved by the student. That means all the knowledge states where B is in become higher likelihood, higher probability. And those which are not in lower probability, because the probability has to sum up to 1. If you take the likelihood, this is not necessary. Problem D is failed. That means that the probability of all those states where problem D is not in has to be increased. And finally, problem E is also solved, and those problems where problem E is in get higher probability, and after 3 steps we will find that all the probability mass is concentrated on this knowledge state. So again, after 3 steps, we have the diagnosis that the student has the knowledge state A, B, C, and E. So the principle is increase likelihoods of all those states which are in accordance with the correct, incorrect answer, and decrease the others. As I told you already, ALEX, the system which is based on knowledge space theory, higher level of knowledge space theory, to be honest. And I give you an example with 6 types of problems in elementary algebra, and this is the precedence or prerequisite relation for these problems if you ask the expert or analyze the problems. And you have to be aware that if I take these examples with only 6 or 5 problems, this is simplification just to make the understanding easy. In reality, of course.
The errors. You now have errors.
Yeah. Very good. Very good remark. Thank you very much for this. Because in the slides before, we had upside down this, and we did not need the errors. That's one of the principles of the Hasse diagram, and you need to know these principles in order to interpret the diagrams correctly. However, in this case, we did not use Hasse diagram, so we need to have the errors, because the most difficult problems is this one, F, and the most easiest problem is A. So A is a prerequisite or precedence item for C, E, D, and F. So if you take it rotating 180 degrees, you can skip the arrows. However, not the lines, please. Thank you for this question.